We start this chapter by talking about Huygens principle. We have all seen a stone drop on the calm surface of water and see the waves progress outwards. So for example, in this figure you can see the waves are going outwards. And what is dropping in the water is just a small drop. So the idea is these waves spread out in water from the point of impact in the outward direction. So the Huygens principle tells us how the next wave forms from the current wave. So the fundamental idea is that the current wave acts as the source of, or you can say point source, for production of spherical secondary waves, which are called wavelets. So let us see this in two special cases. So first we are going to talk about the plane wavefront, and then we will talk about the spherical wavefront. So we first have the plane wave propagation. So in the plane wave propagation, we have the current front is right here, which we are writing as old front. So this is the present front, and we want to form a new front of the plane wave. So what you do is you take a point on this line AA prime and you draw a circle with radius c times delta t, where c is the speed of the wave and delta t is the small time elapsed. So you do that at this point, you do that at another point, you do that at a third point, and then at this maximum point c delta t, at this point, through these 3 points you draw a line, you get BB prime, which is the new wave front. So you could choose any 3 points. In fact, there are infinitely many points here from where you keep drawing circles, and you keep taking the point right here at the top of the circle, and you take a line joining all these top points and you get a plane wave front. So this is the new wave front. Now we talk about spherical wave propagation. So this is the current front in blue. So this is the present front. So we are right here, and this is the new wave front. So how do we go from the old wave front to the new wave front? Again, say c is the speed of the wave. So c is the speed of the wave, and delta t is the small time elapse. So again you draw a circle, and the center is on the old wave front. So you draw the circle with the radius c delta t. Then you draw another circle with again the center at the old wave front. Again the radius is always c delta t. So the radius here is also c delta t. Then you take another point, then again you draw with radius c delta t, and you have all these points. This is the highest point or the most farthest point, and then you draw another circle which envelops all these points. So there are infinitely many points. So you have another point here from where you will draw a circle. There is another point here from where you will draw a circle of radius c delta t. There is another point here from where you will draw a circle of radius c delta t. So on. So all those radiuses will give you these small points corresponding to these centers, and you basically join all these points to get a new wave front. So we have talked about plane wave propagation, and the second one is called spherical wave propagation. Spherical wave propagation. Now we will talk about reflection. So basically we want to prove the law of reflection using Huygens principle. So while using Huygens principle, we are assuming that the light is traveling in a wave form. Just like in the Huygens principle we are using the wave propagation, we are going to use the same property to derive the laws of reflection. The first thing you notice is that the reflected light is in the same medium as the incident light. So the velocity of the light would be the same. So say this is the light. So the light comes in, it falls and it gets reflected. So there is the light coming like this. It's incident at here, then it gets reflected like this. Another beam of light is coming like this, goes all the way down, gets reflected, goes like this. So this is the front. So let us write down the front. So say the front is A1 B. So this is the front of the light, means that there are large number of light rays which are going like this in the form which are coming parallel to each other. So this blue line A1B is the front. So this light wave has already touched the surface, but the light ray here has not touched the surface. It still has to travel some distance. So say it has to travel till point C. Now the light which has touched here will already get reflected. So by the time this light ray goes from A1 to C, this light ray at point B, this would have already traveled to point, say, A2. So we have two right angle triangles. The first triangle is A1, B and C, and the second triangle is A2, B and C. So A1C is equal to A2B. So A1C is equal to A2B. So by the time the light travels from A1 to C, the light after getting reflected has to travel from B to A2. So this is just by reflection. So both of these are right angle triangles because we are talking about wave front. So this is the incident front and this is the reflected front. So we are calling that incident and reflected because there are other light beams also coming in parallelly which we are not drawing. So this front consists of large number of light beams falling parallelly. So you have reflected wave front. So first you get reflection, you have a 90-degree angle, and BC is the common hypotenuse for both the triangles. This is common hypotenuse for both the triangles A1BC and A2BC. So you have the hypotenuse is the same, the right angle, the perpendicular is also the same. So you have two congruent triangles. So you have A1BC, this is congruent to A2BC. So since these two triangles are congruent, you have the angle theta 1 is equal to angle theta 2. So theta 1 is the angle in the triangle. So this comes from A2BC, and theta 2 is the angle in the triangle A1CB. A1CB. So these two angles are equal. So notice that this theta 1 is equal to 90 minus angle of reflection. So theta 1 is 90 minus angle of reflection. So you measure angle of reflection from the normal. So this red line is the normal. this angle is 90 degrees. So this is the angle of reflection. So this angle, which is angle of reflection, so the ray is incident like this. This is the angle of reflection. This is 90 minus angle of reflection is equal to theta 1. Or you can say angle of reflection is equal to 90 minus theta 1. Anyway, theta 1 plus angle of reflection is equal to 90 degrees. Similarly, what is theta 2? Theta 2 is 90 minus angle of incidence. So notice again that angle of incidence is, so this ray is incident here at C. So the angle of incidence is this. This is the angle of incidence. That is between the ray and the normal. So since this ray is parallel to this ray, this is also angle of incidence. So this angle and this angle are the same. But anyway, this angle of incidence plus theta 2 is equal to 90 degrees. Or you can say theta 2 is equal to 90 minus angle of incidence. So since theta 1 is equal to theta 2, you have angle of reflection is equal to angle of incidence. And that is what is the law of reflection. So basically we're talking about wave fronts, that waves move, the wavefront moves at a constant speed of c times delta t. So notice that this wavefront is moving at speed c times delta t. It's a constant. You have to, it just depends upon the wavefront. So this was the old wavefront. You have a constant distance c delta t here, from here c delta t, from this point also c delta t, all points. Similarly here you have a constant distance c delta t. We were able to prove the reflection principle because we said that this wave front will move with a constant speed. So by the time the light goes from A1 to C, this will be the same as the wave front after getting reflected from B goes to A2. So A2B is equal to A1C is actually a consequence of this wave front moving at a constant speed from the previous wave front.